Good morning my dear friends. In today's video, we are going to see some technical questions related to HVAC system design and installation. Let's start the video. So here the first question is related to flexible duct. Sometimes we can see the flexible duct bends are too sharp due to site condition. I mean mainly due to the site classes with the other services. So properly installing the bends will improve the performance of the system. So what is the perfect bend radius for the flexible duct? And the answer here is, if you see here, the right side image for the description, and first thing is good engineering practice is keep bends greater than or equal to 1 duct diameter bend radius. For example, consider we have 150 mm or 6-inch dia flexible duct, and assume that if you put a 6-inch circular duct like you see here, this is just an assumption. So assume that if you put a 6-inch circular duct in the bend of flexible duct as shown in the right side image, that is the perfect way of making the bend radius. So if you're keeping one circular duct here, then how you will bend the flexible duct? So that is the perfect way of making the bend radius for the flexible duct. And the second question is, chilled water pumps in the ETS room or heat exchanger building room, its series are best parallel. So what is the impact in the flow and head? Here the pumps are arranged in a parallel way. So parallel way means there will be a common suction manifold, and after that there will be a common discharge manifold. Okay, so here the total system flow divides at point A. That means that here the total flow comes from here, will be divided here and here and in the suction manifold, and again it is rejoins at a discharge manifold. Okay, and it goes to the system. So here what happened, if there are two operating pumps, the flow is split 50-50%. If there are three operating pumps, the flow is split like 33 and 33 and so on. So well, all the pumps are selected at this reduced percentage of the design flow rate, but the pump head remain at 100% of the design head. Okay, pump head will not change. The flow is the flow we can change like a 50-50 or different percentage based on the number of pumps. And second thing, so in this second case, the pumps are arranged in the series manner. So here first coming to the maintenance point of view, this type of piping arrangement allows either of the pumps to be valved off. I mean we can shut down for maintenance without disturbing the system. Note that for normal series operation, the total flow will pass through each pumps. Okay, so each pump supplies the full design flow rate at half of the design required head. In the parallel arrangement, we can make the flow half, but coming to series arrangement, it is like 1/2 of the required head. Now we will see what is the impact. So as we discussed earlier, pumps in series are connected end to end, each adding head to the system. Well, parallel pumps share a common suction and discharge, adding the flow to the system. So finally, pumps in series, it increases the total dynamic head or pressure, which can be useful for system that require higher pressure, because each additional pump pushes the fluid further along. Well, coming to the parallel, it increases the system flow rate, which is beneficial for system requiring the high flow rate. So here each pumps operate independently, adding its output to the system, resulting in faster flows and higher flows. So this is the main difference if the pumps are arranged in series or less parallel manner in the pump room. And here we have a practical question. A conference room located in the building has 90 feet into 60 feet sizes. It has equally distributed supply duct from the package unit. So the package unit is located in the roof. From there the supply duct is equally distributed in the conference room. And return air is collected via common return plenum. Okay, and there is no return duct in that conference room. So the system with a large ceiling return plenum experience uneven air return characteristics with the resulting high indoor air quality problem, also comfort problem. So the question is there any requirement for ceiling return air plenum? So now let's understand the problem here. So we have the arrangement like this. So here as I shown you, we have the package unit located here. From the unit we have the supply duct which is properly arranged with the square diffusers are there at each branch, and with the proper volume control dampers are there. So coming to the return, we have only one common return air plenum for the full conference room. So the issue is we are getting some indoor air quality issue and comfort problem. So what is the rule, means how many return air plenum we can keep here or here. So what is the rule and how to resolve this issue? So the answer here is, there is no specific rule in the standard to regulate this ceiling return plenum. However, good engineering practice is that when using ceiling space as a return plenum, return air collecting inlets above ceiling must be evenly distributed and not more than 4000 CFM should be collected at any one location. So it is the good engineering practice that if we have like 8000 CFM, means if it is more than 4000 CFM, we can make the additional return air plenum. So it will improve the air, means indoor air quality and proper return air to the system. And the next question is, what is flexible duct inner liner pulling and how it affects the performance of the flexible duct? So flexible duct inner liner pulling means you should not compress the longitude, you should not compress or push the flexible duct inside. Okay, that means you should not perform the longitudinal compression. Instead of that, you need to pull the flexible duct. If the flexible duct pulling is not tight, the friction rate will go very high. For example, in the left side image, the first image you can see, if the flexible duct has 30% of longitudinal compression, okay, so the allowable is 100%, means if you have done only 30% compression, the friction rate 4 times high. Like I mentioned here, it will be 4 times high. Also, if the flexible duct has only 15% compression, the friction rate doubles, like you see here. So the recommendation is 0 to 4% should be followed to reduce the friction. So if the maximum the pulling is like this, means so 0 to 4% we can make the allowance to reduce the friction in the correct way. The next question is, linear slot diffuser used in a VAV system create drift and are making major comfort problem. For example, linear diffuser with a 10 feet length is served by a single duct connection. So let's understand the problem first. So we have a condition like this. So in this arrangement, the if in this arrangement the VAV is located here, and here this is just for example. So AHU is here, from AHU the duct is coming here, and the VAV, after the VAV the duct is passing to the big room, and here this red color what you see here is a linear slot diffuser. The total length of the linear slot diffuser is 10 feet. So this is the condition. And also this duct is moving continuously to serve to the different parts of the room, and we have different slot diffuser. So here the issue is, I have taken only one duct connection to serve 10 feet length linear slot diffuser. So this is the question here, and the answer here is, the first thing related to commissioning, linear diffuser must be utilized with deflection blades, and the deflection blades must be adjusted during the balancing process, okay, for the proper air. Second thing, coming to the design and installation point of view, additionally it is advisable to recur multiple duct connection for every linear diffuser exceeding 4 feet in length. This is the important thing. One connection for each 4 feet section appears to work well, okay, on long length of linear diffuser. Providing this multiple duct connection assures even distribution of air into the linear diffuser plenum. So with one duct connection, maximum length of 4 feet must be followed. So as per SMACNA, what is the maximum sag or deflection, and what is the maximum support spacing length is allowed for the flexible duct? So like you see here, maximum acceptable sag, you can see in this image. So this is the flexible duct, and here is the maximum sag is given. So ½ inch per foot. That means ½ inch per foot means every 1 foot maximum ½ inch sag is allowed. That's the first thing. Maximum spacing of support between flexible duct, like you see here, here one support and here one support. This must not exceed 4 feet for the flexible duct. And here is the practical design question for the VAV design. An office room has design cooling requirement of 650 CFM. So this value we got from the HAP software, and minimum ventilation requirement for that office room as per ASHRAE 62.1 is 1000 CFM. So you need to assume these two values. 650 CFM is the cooling load requirement, airflow, and 100 CFM is the fresh air requirement. So how to select the VAV? So instead of referring only manufacturer catalog, as a design engineer, you have to know how to verify the answer using the formulas, and other design condition also you need to consider, like low pressure drop, low noise, and proper controllability. So now we need to know how to size the VAV, how to select the VAV using some backup formulas. So let's see. And one more important thing is properly sizing the VAV you can see the different questions like when I use the pressure dependent VAV system in a large facility room spaces, it causes large variation in the airflow. So you will get the answer for this question also. And second thing, what are the two types of VAV? This one just the simple concept you need to understand to solve all these questions. And second thing, how to find out the minimum CFM for a VAV terminal box. This is the important question. Which type of VAV I need to use for the higher airflow, whether like pressure dependent or pressure independent. So which one we need to use? So what is the maximum velocity at the VAV inlet is recommended? What is the maximum recommended CFM for the different inlet size of VAV? So for all this question we can find out using the answer which we are going to discuss now. So my primary intention of this question is, so you don't simply open the catalog and select the VAV. So you must know the you must have clear understanding of the VAVs. That's the reason. So coming to the answer here, the first thing is you can see the arrangement. We have the air handling unit here located here, and it's applied to the different VAVs there, because each zone it needs different temperature. Okay, for example, here I need 22, here I need 24, here I need 28, here I need 30, for just for example. So that is the reason I added VAV here. Now let's start the answer. So if you need to know answer for all this technical question, you have to have some basic of 2 points. So what are the two types of VAV? So there are two major classifications of VAV we have, a VAV box and VAV terminal, that is pressure dependent and pressure independent. So a VAV box is considered pressure dependent when the flow rate passing through the box vary with the inlet pressure on the supply duct. So let me tell you one example. You can see here, for example, if all the people in the home use washing machine, shower and dishwasher in the same time, you can see the pressure gets lower in the plumbing system. So when you use all this sanitary fixture and accessories, the pressure in the pumping system is it will go lower. Okay, so we can see the similar type of effect in the pressure dependent VAV. So like for example here, in a HVAC there is a conference room and it suddenly needs a lot of air because of the meeting or some other purpose. So what happens, the damper fully opens to pass all the air in that room. And the important thing is, in pressure dependent VAV, if there are other offices also connect in the same ductwork. Okay, so like you see here, the same ductwork, all the offices, all the rooms are connected. Suppose if I have like around 20 people here, I am going to have higher flow rate, means this VAV will open, this damper will open, and I will get higher flow rate. So now let's see the condition. So if there are other offices in the same ductwork, and if the airflow in the conference room goes up, then the airflow in the offices will go down because they are dependent on pressure. So simply saying, airflow depends on pressure for the pressure dependent VAV. Okay, so coming to pressure independent VAV, which has flow sensor that measure the pressure in the box, I mean the terminal box or VAV box, and that sends the information to the controller which is located in the part of the VAV. The controller can calculate the airflow and control the damper, I mean open or close or to adjust for changes in a pressure in the system. Simply saying, CFM stays the same when the pressure changes, and CFM will change when you go from one set point, I mean the temperature, to another set point temperature. Okay, so the main difference between these two types is flow sensor and controller. So if you try to plot a graph for this pressure independent VAV, suppose consider this X direction we have the flow and this Y direction we have the pressure, then the graph will be like the straight line like this. That means when the pressure is changing from here to here, the flow will not change, it will be same. Okay, it is irrespective of the pressure in the duct system. Okay, that is called as a pressure independent VAV. It will change based on the temperature set point from one set point to another set point for the pressure independent VAV. So normally each manufacturer provides the limit for VAV box from minimum to maximum CFM. Like you see here, I have taken one model. So for this 125 mm inlet opening, that means this is the inlet opening for the VAV where the duct is connected. Okay, so for this point the minimum and maximum is 0 to 300 CFM you can adjust, and similarly for the 1 to 140 inlet opening, 158 till 400 mm they have given with a different CFM. Okay, so now here the point is, normally here you can see here the actuator or the controller is located, and inside there will be a damper, and this is the sensor point, flow sensor point for the VAV. So the first point we have to see here is how to find out this minimum CFM for the VAV. Okay, so minimum CFM is based on what VAV controller can read as a minimum pressure differential signal from the flow sensor. So here if you see, in the inlet there is a arrow cross type, 4 ports are there. This is used to measure the total pressure, and the back side of this VAV we can see the 2 port. Here we have 4 port, in the back side we will see 2 port, that is used to measure the static pressure. So inlet for to measure the total pressure, and the outlet it is used to measure the static pressure. Here the delta P is difference between two signals. As I told you, it is a difference between the total pressure which is measured in the inlet and the static pressure which is measured in the outlet. Normally this pressure differential, the minimum pressure differential that a pressure transducer can read is 0.01 inch or sometimes 0.03 inch. So if you are going lower than this one, the pressure transducer cannot read the pressure differential. Okay, so there should be normally 0.01 inch or 0.03 inch is a minimum pressure differential. So manufacturer amplify the flow sensor this signal, so lower CFM can be possible. So this is another option. So manufacturer uses the amplifier to make the pressure differential high, so they can go very lower CFM also. Okay, so now in our case we are not going very deep into this concept. This one we will discuss very deep detail about VAV and CAV design from basics to the advanced level. I will create a separate video for that. So velocity is equal to, this is the formula we need to know, velocity is equal to 4005 into square root of velocity pressure. So assume we have a 8-inch inlet VAV, the size of the inlet, the circle, that is the 8-inch VAV, and the minimum pressure differential is 0.08 for one manufacturer, the manufacturer called as A. So V is equal to 4005 into square root of 0.08 inch. We will get the answer in feet per minute. It's a velocity. Okay. So now we need to know that 8-inch VAV box, what is the lowest level of CFM it can measure. So lowest CFM is equal to 1133, that is the velocity, into area, because this is the circle. No? So area is equal to pi by 4 into dia square. So pi means 3.14 divided by 4 into the means the circle dia is 8. So 8 square divided by 144, because I want to convert that unit. Okay. So here 1133 into this answer will give you 0.349. The answer is 395 pm. Round up to 400 CFM. Now this is for the 8-inch inlet VAV. Now if you see this catalog, okay, so here you can see for the 8-inch means 200 mm. So the minimum flow the VAV can measure is 400 and it is maximum is 800 mm. So we got the answer of 395 mm. So every manufacturer has the minimum pressure differential with a different value. So we need to know that value to decide that their VFT, their VAV can go at what is the minimum flow and what is the maximum flow. So in this example, I consider 0.08 is the pressure differential between the inlet and outlet. Okay, if some manufacturer follows lower than this value, then of course they can go with the lowest CFM. Okay, lesser than 400 CFM for the same of 8-inch. Okay, that varies between the manufacturer to manufacturer. So here the first question is, what is the minimum recommended airflow for the VAV? So for many years, this minimum airflow were based on inlet sensor signal of 0.03. So last example, just now we saw 0.08 and we got some answer. So for many years, we were using 0.030 inch of water column, and now most manufacturers use the minimum sensor signal of 0.010 water column. That means the CFM we can go low. So normally what happen? So if you follow this low level 0.010 pressure differential for the sensor, then for the 4-inch dia you can go the minimum CFM till 30 CFM. For the 5-inch 40, 6-inch 45. So this chart you can follow to understand how the VAV minimum CFM comes out. And this is based on 0.01 inch of water column pressure differential. And the next question is, what is the maximum inlet velocity at the VAV inlet is recommended? So it is recommended to size the maximum inlet velocity not exceeding 2000 feet per minute. Air moving at velocity more than this value across the VAV will generate the noise in the ductwork, and by keeping our maximum inlet velocity below this limit, I mean less than 2000 feet per minute, we will not oversize the VAV inlet. Okay, and also we will have good airflow control at a turn down. It also reduces the pressure drop. So in our design for the branch, we will try to make the velocity as near as 2000 feet per minute, may even lower than also okay, but not exceeding 2000 FPM. So the question is, what is the maximum airflow Okay, so as discussed now, maximum air volume by inlet size by considering maximum airflow limit using considering pressure drop and noise level. Okay, if you follow 2000 feet per minute as a maximum velocity, then you will get this answer. For 4 inch maximum 175, 5 inch 275. And if you need to know how I got this answer, just now we discussed one formula. Velocity is equal to 4005 square root of velocity pressure. Okay, so we can use the pressure differential and we can get the velocity. And if you follow the velocity maximum of 2000 feet per minute, then you will get the VAV maximum CFM with this limit. So first we find the minimum flow and now we find the maximum flow. I combined both. Now we can find the answer for our question. So in our question, the first one I asked you, the flow in our case is 650 CFM and the minimum ventilation for the fresh air it is 100 CFM. So we have to combine to 100 CFM as well as 650 CFM to select the correct VAV for my application. So coming to this one, you can see here. So okay, you can see here 8-inch dia. 90 to 700. Then for in our case I need minimum 100 CFM for the fresh air and the supply flow requirement is 650 CFM. So I can choose the 8-inch size VAV for my application. So this case I combine to maximum velocity and also the pressure differential of 0.01 inch for this manufacturer I consider. If your manufacturer has 0.03, then this value will slightly vary. So now coming to the next important question. For example, in this area, I need 5000 CFM. Okay, 5000 CFM I need. So can I provide only one VAV for this 5000 CFM or I need to provide multiple VAV? So how to select the VAV? So the answer here is, it is recommended that maximum 2000 CFM from through any single unit. So large unit creates a concentrated noise sources above the ceiling, because normally if the VAV is located above the ceiling, it will create some noises. If we have high flow air requirement, split the zone and use 2 smaller units instead of single unit. And finally, I finish this video with asking a question to you. So we have a mechanical room located here in the ground floor, and here we have the AHU unit. This unit is supplying the supply air to this room. Okay, so now the first I will explain some problems and answer for this one I will explain from the next video. I mean the part 2 video. So the first thing you can see here, over the mechanical room there's a stairs. So you know that the first thing you can see the stairs at the top of the roof floor plan. That's the obstruction number 1. Now we are limited to take all the duct through the right side of the mechanical room, because you know that we cannot take any supply or return duct through the stairs like this. Okay, so now we are allowed to take the duct only from the right side. I mean through this area. Through this area only we can take all the ducts. So this is the obstruction number 1. But wait, it will be very easy if I add only this condition. So let's look at the next image for the another twist. So here is the another twist here. So look at a little closer. I mean the left image, what you see here, mainly this red color. Okay, so and you see the obstruction number 2. It's a flush beam at the same level. That means at the same level of the ceiling joist around it. Like you see here, we have the flush beam. That means that's shown by the horizontal red line above. Okay, a flush beam image shown in the right side, which limits the vertical space available to move the duct through the area right side of the room. That means here all this area I have the flush beam. Okay, so we have the section like this and the ceiling is here, the flush beam is here. So very limited space I have here to pass all the duct. First of all, this is not a simple room. I can pass only one small 150 by 150 duct. This is a mechanical room. I mean the AH is there. So this is the main source. From here I need to pass all the duct to the room, and this is the area I need to get all the duct, return duct to the room. So this is the important thing for us as a mechanical engineer. So I will start the next part with this video. So if you want this type of video related to HVAC design and installation technical questions, so you can please don't forget to add your comment in the comment section. Then only I can understand and I can post more video like this. Okay, so we will see again in the part 2 for the HVAC technical questions. So till then, bye bye, see you.